Good morning. So we're going to continue learning about C++ and some of the differences between this programming language and what you've learned so far in C. And our goal is to first continue to go over how you would do tasks that you've already done in C++. And then we're going to learn how to build upon that to build on this idea of object-oriented programming further. So if you remember from when we were building up this idea of compilers, and we were learning about how to, hold on for a second. We were learning about how to fill in information. And we ran into this problem when we were compiling, where we had, if you tried to using an integer in a header file, it would make duplicate copies and we didn't like that. And so we used this #define variable in order to be able to fill in all this information. So this is what we ran into before. The crucial thing is that we solved this problem. So what I just said is this duplicate register allocation. And so that's why we get these compiler errors. And so we use this #define directive to get around this issue. So the question becomes, now that we're moving into object-oriented programming, is there even a better way to do this? So remember from, we had this issue, okay. So we had this issue where if we had a header file and it was included in both main and in the .c file, well, factorial bad.h was included in factorial, in fact, bad.c, and in the main function, that it made a duplicate, and we got around this using #define. Okay, my animation's really, okay. So in C++, they recognize that we still want to have the variable types, that these variable types are very useful. And so what they have introduced is the use of const in header files. And so what I can do is I can create a double, for example here, I can create a double. And so this is in the C version where we use #define. And then in C++, I can do the exact same thing in the .header file by saying const double pi equals 3.14159, the semicolon after it. And the reason I can do this is because the const is short for a constant. That variable is always the same. And so when it is defined by the compiler, it only creates it once. There's no reason for duplicates because I can make that a constant value and it only makes one copy. So therefore, when you use it, it will work. Does that make sense? So we start to get around a little of this. Furthermore, in C++, we're going to prefer to use const instead of #define. So that allows us to explicitly define the types instead of allowing the computer to do that for us. The second thing is that we can actually limit the rules. We can limit when and where these variables are allowed. So if you remember, we had this global variable. And if I had #define, it was just a compiler directive and we would fill that in there and then we'd let the computer do the rest. Here we can create a variable name and use that everywhere as a global variable. But because it is const, it's much more effective than using the #define directive. Furthermore, #define directives can only convey what we can convey in characters. So for example, I could define a string, I could define a float, I could define a double, and that was that. With const, I can define pretty much any type I want. The crucial rule is one, make sure you move the stool instead of holding it. The second rule is that you can define anything you want as long as it stays constant throughout the entire program as a constant variable. And so we are going to, I'm going to show you some code And we're going to call this in multiple places and multiple functions throughout this particular function. So first I have in the file const.cpp. I have main, and then I have a double radius, and then I do standard C out. This circle's radius is radius, and then I say the value of pi is pi. Now here we don't see anything defined as pi, but we see that there's a pound include const func.h that can lead us to see what that is. And then the area of the circle, and I have this function circle area radius, and you see that I'm printing it out to the user from that line. I don't have to use any overloaded operators. I don't have to define everything. The object-oriented nature of C++ will allow me to just fill that in, and it will create a string to put onto the data sheet for us. So it's doing a lot of the work on that end. And then I have another function, circle circumference radius, and it calls there. So here's how we're actually making this work. In const func.h, you will see that after I protect the header file, that I have a const double pi right here. And the difference between, another difference between this and the define directive is that if you remember in the define directive, you don't have a semicolon afterwards. C++ requires that we have a semicolon afterwards when we define const variables. So here I have double circle, double radius, and then I also have circle circumference, and they're both returning doubles. And then in const func.cpp, by including const func.h, I'm including that const variable. In C, this would be problematic. We would make multiple copies, and we couldn't do it. In CPP, C++, we can do this, and we'll make one copy. And so in double circle area, I pass radius, and then I have pi times radius times radius. So I have the global variable, I have one copy, and I've maintained the integrity of the data. So that way, I'm multiplying a double by a double by a double. So therefore, I don't have to worry about any inaccuracy. I know the level of precision is consistent throughout the entire operation. Okay. And so what happens is I run this code. I run make const. And then, just like in C, I'm compiling both the library and the main file. I'm just using the new flags. And then when I run const, we'll see that I get the results. Does anybody have any questions about that before I continue? Yes. No, it does not. But sometimes it is considered to be good practice, though. But it will compile if you don't. All right, let me check the chat real quick, see if we don't have any questions in the chat. So here is everything I was just showing you. There's the output. Okay, next thing, fscanf and that gets. You've been working on these homework assignments, and the most common struggle was trying to figure out when I should call by reference, when I should pass by reference. Is it a string? Is it a variable? Do I need to put an ampersand? And that was a very procedural aspect of it because C was making you think about what was going on physically inside the computer. In C++, it's going to abstract some of that complexity away. We're not going to use this fscanf. What we're going to do is we are going to see if we can actually just read it in with a standard input. And then we pass that variable to the object, and it's going to do the work for us. So we're going to get away from this fscanf and get C. And we're going to use standard C in. So standard C out was the C equivalent of fprintf. And standard C in is the equivalent of fscanf. So we're reading in from the command line. The other thing is the signs that you need to use. So standard C out, think of it that the computer is here, and if you want to print it to the output, you're going to the left. But if you want to read from the computer, you want it to go to the right. Furthermore, we have error checking. And I'm going to say that it provides partial error checking, and I'm going to describe what I mean by that in a moment. But here, what I have is an if statement, standard CN variable. So here is one of the benefits of object-oriented programming. What this code is doing is it's saying, I'm going to use the C++ version of fscanf, standard CN, and I'm going to read it into a variable. No more ampersands, no more pointers. I'm reading it into this variable here. The other thing that it does is it returns a Boolean. So this is what's known as an operator, and it's a type of function. We're going to learn a lot more about this later in this course. So it's an operator that takes in two inputs, standard CN and variable. And if what we've been trying to put in is a valid, whatever the type is, it will return true. If it doesn't, it will return false. And this is very beneficial for us. If we have a file with a set of integers, we can say while standard in, standard cin, temp int, and the moment we reach the end of the file, it's no longer going to be a valid integer, which means it will stop running the program. So we can use this standard CN from the IOStream library to not just read in variables and abstract some of this pointer complexity away. We can use it for error checking to be able to maintain positive flow of our program. Does anybody have any questions about this so far? Check. All right, so what I would like to do is I'd like to show you this next file, cn.cpp. And here I have two libraries, IOStream and C standard library. So C standard library is the equivalent of standard library.h from C. It makes sense, C standard library. I'm actually creating a C++ version, and it takes in all the libraries that we could use for C standard lib. So we could do things like malloc and free. We could do exit. We'll terminate the program if it doesn't work. And then IOStream has standard io.h plus all of the operators for the IOStream for C++. So now let's go to main. And in main, I have three variables, temp x, an unsigned integer, unsig x, and float y. Then I say input an integer, and then I have this if statement, if standard cn reads into temp x. And if it's false, I'm going to say it's not a valid integer, and we're going to terminate the program. So first, what I'm going to do before we continue, I'm going to run clear and then make cn. And then the first thing I'm going to do, I'm going to say input an integer. And then I'm going to go, blah, 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 right? Now take a look at what it returned. 0 is not a valid integer. What the program is doing is it returning false, and it says, well, you didn't give me a valid integer, so I'm going to put the value to 0. Everybody see that? So let me go back to the code and show you what that's doing. So in this piece of code, I read in from the command line. I checked a Boolean, and it says, if standard C out, the integer is temp x. Otherwise, standard C error, temp x is not a valid end line. So if you remember, I had that fprintf standard, I had the error command line. Here I do exit -1, and that terminates the program. Then I can continue here, input an unsigned integer, and then it does the exact same thing. So let me run this program again. I'm going to say 100, so it's valid, it's correctly determined this. And let's say I say -100. Look at that. Remember what I was just saying about partial checking? Does anybody have a guess as to why the program did that? So I put in something that's not a valid unsigned integer, and it gave me the valid result and this large number here. Does anybody have a guess as to why? Yes, Jake. Exactly right. So we do the 2's complement of -100. It stores it in there, and it goes, that's a huge number. So that did the same thing. I told you all about the Gandhi civilization error, right? We just did the exact same thing. We just made Gandhi a bloodthirsty tyrant. So I'm going to enter in a valid float, and it works. So what it will catch, so I do 100, let's say I do 11.1.3. And here what it does is it cuts everything off. So it just grabs the first unsigned integer, and then it takes the next part, 0.1, and puts it into the float. Everybody see that? So remember when I went over this whole thing about in C++, it's really good, it can be really easy, but if you don't know exactly what you're doing, it can kind of blow your leg off. I was pointing beyond a structure. So you just saw your first example of it. A lot easier, we don't have to deal with those pesky pointers, but those pesky pointers provide you a lot of security. So let's take a look at some modified code. So there's the scene example, there's the output results. So I hit this thing, what do I mean by partial? It's good for catching values outside of numbers, but accidentally putting in float instead of an integer cause problems, and I just showed you an example of that. So how can we make a better test? And we can do this with C++ strings. So we learned about C strings, which are character arrays. And we learned a little bit about this idea of the string library. And from there we had string concatenate, string compare, we had string copy, and we got a little taste of these libraries. In C++, the string library is robust and very useful. I'm going to show you an example of how we can use the C++ string library to perform the type of error checking that we need. So to do this, the C++ header library is pound include string. So instead of string.h, you're just doing pound include string. The next thing we're going to discuss is this idea of a string stream. And so that's pound include S stream. And so with a input from the command line, we had standard in and C. We have standard CN in C++. But what if I stored everything in a string and then wanted to read from that string and interpret it character by character? In C++, what we'd have to do is we have to pass it by reference, we have to pass the length, we have to go through each individual character, and we saw examples of that when we went to the man pages, right? In C++, we can use a string stream to help us read in information to try to take in an input from the entire string. It's not just going to cut things off. It's going to try to read the entire string that we read in there to be able to determine what's going on here. So an input stream combination, I have int temp and I have standard colon string, stry. I have standard cout and I say input an integer. And then what I do is I read into the string. I don't read into an integer, I read it to a string. And so then I get the entire input from the user into one line, right? Everything until a space. And then I do standard string stream, and that string, I will try to read that whole string into the temp integer. So if I did 11.1.3, now I'm trying to convert that string of ASCII characters into a valid int. Hey, does anybody have any questions about this so far? So now what I want to do is now we're going to figure out how to go through a string and do a test. I'm going to show you a test I wrote that allows us to be able to test for valid integers. So in C, we had to iterate through the entire character array. And in C++, we still have to do that. But here's the thing. C++ has functions that allow you to operate on the object and do that for you, abstracting the complexity away from the user. So in C++, what we can do is we can create a string, and I read into the string, and if I say .find, period, then I can find the location where a period exists in the string. Now here's the things. The C++ library is robust, and I have a specific keyword, end position, that stands for no position. So if I say standard string, which is where the library it comes from, and then I do this again, and we say if standard string find period equals standard string string NPOS, that means that the period does not exist in the string. And that simplifies what we'd have to do in C, which is we'd have to iterate through the whole thing. And if the current character was equivalent to period, we would break the for loop. Okay, so anybody have any questions about this? Okay, so now I have a function no bad cares. Let me go to the actual, okay, cin string. So if I go to the file cnstring.cpp, you'll see that I have included two more libraries, string and stream. And so first I'd like to go down to main and show you what we do there. So in main, what I'm doing is I've created, instead of 3 variables, I've created 6. I've created a string for each variable, and I've created the variables themselves. So we have string x, temp x, string unsigned x, and then string float x, and then I have float y there. So I say input an integer, and now what I'm going to do is I'm going to input it into a string. Then I have standard string stream. And I put the string into it, and then I read it into temp x. So now what it's doing is it's trying to perform the check. So now what I do is I start adding little tests onto this where I can take this string and check for it. So first, in an integer, I should not have a period, right? So if the period is there, it's automatically going to say it's false. So I can put in as many periods as I want, and it will work. I also have this function, no bad cares, that I've written. So now what I'd like to do is I'd like to show you this function to show you how I've supplemented the string stream. And so here's no bad cares. And Dr. Morrison was good about memory. He would call it by reference. So we're only passing a pointer, not a full copy. So we'll fix that. But now what we're doing is we're calling string by reference. And what I'm going to do here is, because we're calling by reference in CPP, all I have to do is make that one minor change, and I don't have to change any of the other code in my function. So that's one of the things about abstracting complexity from the user. So here I have an unsigned int, and I'm iterating through the length of the string. And here, I would say if the string is outside of the character, so what I've done is I've said if it's less than 0 or greater than 9, then I have a potential bad character. And then I say if the string at that line is negative, then I say if the negative is not 0, then I return false. So I'm allowed to have a negative at the very beginning of the string. Does everybody see that? So what we're doing here is I'm saying if I have a negative anywhere else in this input, it will return false. Also, if I have a period here, I can put that there too. But I also have that check outside, so either of those tests is sufficient. So I'm going to return true. And now I have standard string stream and fine for the integer. And now once I get through all there, I can put it in. Otherwise, I say it's not a valid integer and I print it to the output. Then I have unsigned integer. And then I say I don't want any periods or negative. So negative 100 will not pass this test, which is what we want. And then for a float, I just get rid of those requirements and the float is there. So what I'm going to do is I'm going to make cn string. Let me run clear so we can see it. And if I put in negative 100, this will work. If I put in negative 100 for the unsigned integer, it doesn't work. So now we've used this string library to be able to improve upon the normal. So we have negative 100. If I have 105, 3.1, A, I put about invalid character in there, and now we are right now we're cooking with gas. Now we're moving along here. So here's all the code that I just showed you. And there's the output. Okay, so now we figured out how to modify, with our knowledge of string libraries, how to reduce the complexity of all this work that you've been doing in terms of being able to read in from files or read in from the command line. But we also saw that if you're not careful about it, it can really blow up on you. And that's an example of why it's important to learn C first before we learn C++. Because now you see, all right, I understand what's actually going on here. I understand why that code wasn't quite working. I understand how that's characters work. I understand how the pointers work. I understand why it is that we have to be very careful about all these things. And then once we do that and we implement it in C++, now I know why that went wrong and I can make a quick modification in the library. Now here's another thing about C++ that's really interesting. We'll drive a lot about what we're going to learn about for the rest of the semester. what happens if I want in C, what would I have to do if I wanted to print, and I wanted to print the exact same thing, except I had different types. So I wanted to print out an int, I wanted to print out a float, and I wanted to print out a double, and I wanted to write a function that did this. And I only want the function to only print out the integer, I only want the function to print out the float, and I only want the function to print out the double. How many functions would I have to write to do that? Don't take a guess. 3, very good. Yeah, very easy. We have to write 3 because we can't make any changes for this. But in C++, what if I told you that to do this task, we only have to do it with 1? And to do this, we're going to use what's known as templates. A template allows us to pass a variable type as a parameter to a function. So it's not just that we would say unsigned int and then variable name or float or student from the struct that you created. Now we can say, I can make this work for any type that I want. And so this is known as a template. And we say that function templates are special functions that can operate with generic types. So as long, what the compiler is going to do is it's going to see the generic type name and then replace it with whatever we use to call it. So if I have the generic type name and then I call that function with an int, the compiler will make a copy of that code with an int for you. It will treat the function like an object, and then we'll make everything else work to reduce the complexity of your code. This allows us to create a function template whose functionality can be adapted to more than one type or class, and we're going to learn about classes later, without repeating the entire code for each type. So now we've cut our work down. Two crucial terms that I'd like you to understand going forward. So you're going to hear me say this a lot, this idea of a template parameter. A parameter that can be used to pass a type as an argument. And the generic type is the type identifier of that template parameter in code. And so when I show you a template function, I'm going to identify that these are template parameters. And then the generic type, I will differentiate between these two. All right, so before I go to the animation, so the way it works is we use the keyword template, and then we use less than symbol, and then a class identifier. And we would say template class T, for example, or template class gen for generic, or we could say template type name identifier. And those can be generally interchanged. And so let me show you the example, and I'm going to define what is the template parameter and what the generic type is. So here I have a function. The function is print function. And at the beginning, I have template class T. The template parameter is template class T. And the generic identifier itself is T. And we see that in print function, I have T space T underscore variable. And what happens is when I call the function, the compiler will identify the variable type and fill it in. It will replace the generic identifier with an int, a float, a string, a student. Once we determine ways to print that out, it will do the work for you. So here is the template class identifier. The function uses the class identifier, the generic, to call the type. And so if we used, okay, so here's another thing. So first let me go to make template and let me hide. So I'm going to do something that you're probably going to really enjoy. You dealt with all these annoying char stars, right? And we did this in C and it caused us several issues. Remember that memory mapping problem that we had? So if I save this and update it to FileZilla, and I try to run make template, it's not going to work. Because it identified the issue in C that if you weren't careful with char star, that this could run into serious memory mapping issues. So it's like, we're not even going to let you do that. So the compiler error states deprecated conversion from string constant to char star. In C++, it's not allowed because it's unsafe. So what we've done instead in C++ is we have, let me go back to the top. We have a standard string and that we can save as Go Irish. So now we're saving a character array, but it's using what's known as a class to save that in a specific way that's safe, and we can perform operations on it. The next thing I do is I call print func I, print func j, and print func k. So I'm calling the same function with 3 different variable types. Now, in C, this would have been a problem, but in C++, it's not that much of an issue. And by the way, both of these work, but you'll see this format much more consistently in code and industry. So I have template class T, print func, and I replace T with whatever the function call is. This could be, if I said gen or generic, that would work. I could call it whatever I want. I could call this I do what I want, and I could use that. And so the thing is, when I call the functions, it will replace it. Do make template. I do what I want. It works. It compiles. Yes. So I'm going to get to that. The return types must be consistent. So that's the short version, but I do have that in a future slide. So before I run it, let me show you what happens, what's going on underneath the hood in the compiler. So we've changed it to standard string. We've discussed this. And then underneath the hood, what's going to happen is when I call print func I, that's an integer. So it's going to replace T with a version of the code, an int. And that's what it's going to put on the instruction stack. And then when I call it print func with double, it's going to do the exact same thing. And then with a standard string, it's going to do the exact same thing as well. And so it's going to put those versions of the code. So the purpose of templates is so that you don't need to constantly write different versions of code in order to do the same task. So it's saying we are going to say if you can do a task and it can be done on a type of object, then we will let the object do it for you. And so now with I do what I want, I'm going to run template. And so I called it whatever I wanted to call it. And now it prints out 1842, 3.14, and Go Irish. Does anybody have any questions about this before I continue? Let me check the chat as well. I don't see anything in the chat. All right. The last thing that I'd like to talk about is getting more around this idea of arrays. So in C, we had to use malloc we had to allocate the size, we had to free it afterwards, and it was kind of obnoxious. But it's very procedural, and you have a strong understanding of why it is that we need to free memory. So you want your memory usage to be efficient. Particularly electrical engineers, chemical engineers, mechanical engineers, aerospace engineers, scientific computing, you will often use embedded environments where the memory is limited. So having that strong understanding of how that works will really benefit you in your career. And now in C++, it's like, all right, let's take away some of that, let's abstract some of that complexity for you. And furthermore, let me write a program and a class that allows you to be able to put as many elements into this array as you want. And we're going to call that a dynamic array. And it's going to abstract the complexity of allocating all that memory for the user. We are going to do this, and we're just going to call it a vector. So the arrays are good, but as you learn from working in C++, they can often be bad. We have dynamic memory allocation, array index, that's out of bounds. We have this segfault. This is another crucial thing. We're going to see this in a moment. Remember, you run into these segfault problems? So standard vector is going to come up with another way to help protect your memory. If you call an out of bounds element, instead of going through a segfault, it's going to throw an exception, what's known as an exception, and tell you that you have called something out of range. Here you have you can accidentally reallocate memory if not inserted individually, and we saw an example of how C++ no longer permits that by deprecating char star from the C++ library. In C++, it's known as a vector. And so the way we're going to do this is we're going to have a library pound include vector. And standard vector, and we're going to template it. So we can make the array whatever we want, and we're going to say standard vector, and then have a template there as an integer, and here I call it the int vector, and I can do it to whatever I want. If I use this, and I don't put any parentheses after it, then by default, it will make the array a length of 0. But I can make the array as long as I want. And that's what's going on here in the second line. I have standard vector int, and I'm making it a length of 12. So I have 12 locations in memory that I can use. Does everybody see that? There are other things I can do. I can also tell the computer what I want the initial values to be. So if I have 2 in the parentheses, I'm going to have, here I have 12 and -1, right? That means it's going to create 12 integers, an array of 12 integers, all of which are defined initially as -1. So I can get rid of that issue that we saw in C, that if you don't define anything, you're dependent upon the previous values, right? We saw that as an exam. We even had an exam question on it. And because of templating, I can do the same thing. I have standard vector, and inside the braces, I have standard string. I've created 10 strings, and I've made them all Bob by default. So I print them out, just Bob, 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 right? Another thing, .at function. So I was alluding to this a few slides ago. If I had 10 elements in a vector, and I tried to access if I had 10 elements in an array, and I tried accessing the 15th element, I would get a segmentation flaw. The vector library has what we're going to call a method, .at. And I pass that number there. And not only does that return the value if we have a valid element, but the .at provides error check and make sure that you can't try to access a value outside of the bound of the array. Yeah, does everybody understand that so far? So .at provides some security. And now, here's the benefit of using standard vector, is that if I say I initialize having 4 elements, and I can put in 4 elements, and then I reach the end of the array. In C, we're done. Can't do anything else. In C++ vector, it's going to go, you know what? I am going to allocate double that size and then put the next element in there. And the method I'm going to show you that does this is called pushback. And so here's all the pushback method. I described this in detail. It'll automatically grow larger as we put that onto the end. So here I have IRIQSH. And so if I'm printing out a string and it's empty initially, the strings would then say I, R, I, Q, S, and H. And so here's another thing that's beneficial for vectors. In C, if we did this, we are kind of out of luck. We've just permanently misspelled Irish. But in C++, we can use a method called erase. And what we'd have to do in C is we'd have to allocate a new array, go through each element, and then at the specific element, we'd skip it, and then allocate the new thing. In C++, it does this, but it abstracts the complexity for you. So here, name.begin is a pointer to the beginning of the array, and then it's +3. Because you studied C, you understand why we can do +3. Because that's 3 times the size of the element. This allows us to be able to perform this task. So C++ is still doing that kind of benefit for us. And so if I do name begin dot +3, what will happen is I will add 3, and then I'll reallocate memory, but deliberately leave out that particular element. And now we have Irish there. Okay, does everybody see that? So here, I'm going to show you some code that I've written that puts in vectors. So here I have a vector of characters. I call it equal vec. Oh yeah, here's another cool thing. So in C, if I wanted to create an array that was equivalent to another array, I'd have to allocate the memory, I'd have to iterate through, I'd have to do all that work, right? In C++, I can create a new vector that I call equal vec and just set it equal to a previous vector. And it does all that work for you. Does everybody see that? So here, what I'm going to do is I'm going to create a vector, and then I'm going to push a number of characters onto the new vector. And if you've done the memory allocation right, the old vector should not remain unchanged, and the new vector will have a new set of characters. So I made this last year. Notre Dame beat USC 30-27 that year, so I did that. This year, we're not even playing them. So, all right, so another thing. Here, what I'm doing is I'm iterating through. I've created an array of 12 elements. All of them initially are -5. And then I iterate from 0 to 9, and I say integers.add_i is 2 times I, right? So it becomes 0, 2, 4, and we go all the way up to 18. And because we didn't hit the last 2, those last 2 elements are still -5. Does everybody see that? And so let me show you, I'm going to show you this vector.cpp code, and this is how we'll conclude lecture. There it is. Okay, so first let me go down to main. And so what I do is I create a vector main. And then I push back those characters as I showed you. I'm going to print the elements. I'm going to show you how I do that in a moment. Then I erase that character and I do it again. And then I create another vector that's equal to the first one. And then I push back all those characters that I've shown you. And then I print name and equal vector. The first one will print Irish. The second one will print Irish 30 USC 27. And then I'm going to do the same thing with 12 and 5. And then I'm going to print vec elements. And then the last thing I want to ask you, so it's the same string. So I have the 12 vectors. I have 0, 2, 4, 6, and all the way through 18, -5, and -5. So when I run pushback 1842, where do you think this is going to end up? Where do you think it's going to end in the vector? What location? Yes. On the end, after the two -5s, right? That's exactly what's going to happen. And then I'm going to print these vector elements. In this function here, what I'm doing is I call the generic type. I call this generic vector, so I can do this for both int, string, and character vectors. And then I just print the element there, and then it runs. So I'm going to run make vector, and after this, I'm going to conclude lecture. So I run make vector, and we see that we initially had IRIQSH. After I deleted it, it's Irish. Then I printed the original and the new one. So we see that we properly allocated the memory. They're all originally -5. Just like we predicted, we had two -5s left. And also just like we predicted, 1842 is after the -5s. All right, so on that note, it is time to go. I will see you all for Lab Friday on Friday.